All right. Thank you, Olga. So I will continue with what is essential to know in compressive sensing. So yesterday I have given you some guarantees, theoretical guarantees for the success of several algorithms, L1 minimization in particular, iterative R thresholding, orthogonal matching pursuits. Some of them were based on coherence, but with the coherence we don't break the quadratic barrier. And there was a concept of restricted isometry property. So when restricted isometry constants are small, that guarantees sparse recovery via various algorithms. But I haven't told you, given you an examples of matrices which satisfy those, have small restricted isometry constants. So this is what we want to do today. And for the optimal regime of parameters, these matrices will be random matrices. Right? So what I want to do today is prove this RIP for random matrices, for first of all Gaussian matrices. Okay, so it'll be in three parts, the argument, and it starts from a concentration inequality. So what is the setup is that we have A. Recall that I use the notation M for the number of rows because I identify that as a number of measurements, M for measurements, and capital N is a large number, so it's the dimension of the vectors we try to recover. So the entries of A will be taken to be independent random variables, normally distributed with mean 0, so variance 1, and we need a proper normalization. The proper normalization to satisfy the restricted isometry property is 1 over the square root of M. Okay, so let's see why 1 over the square root of M. Well, first of all, we need, we want to prove the restricted isometry property. So in particular, if here we're going to take X to be one of the basis vector, Ej, this A of X will be a column of X that has to have norm close to 1. But so what is, in general, if we look at the norm of A times X, well, when X is a sparse vector, we want that to be close to the norm of X, some squares at the appropriate places. But if I'm looking at the I entry of the matrix A times the vector X, again, I fix the vector X at the start here. This is the sum of the Aij times Xj. And here the randomness is in the Aij. Now this is a random variable. In fact, it's a linear combination of Gaussian, so it is Gaussian, and the random variables that appears here are independent. In particular, the variance of this linear combination is the sum of the variance of that. So the Xj, which is fixed, will come out of the square here, and then the variance of the Aij is 1 over M due to the normalization. Okay, so this is the expectation of the square of the entries number I, does not depend on I, and when you sum over all I, you get the expectation of the L2 norm squared of AX. Sum over I from 1 to M of that, you got the norm of X squared. All right, so that explains you already why we take this normalization 1 over square root of M. All right, so we know that the expectation of A of X squared is the norm of X squared. We want, in fact, something a little stronger than that. Well, we want that this quantity concentrates around its means. In other words, we want that for a given t between 0 and 1, the probability that A of X squared minus X squared in norm, so this difference in absolute value, I want that to be small. So the probability that it's larger than t times the norm of X squared should be small, the failure probability, so should be smaller than exponential of minus something that, minus ct squared of M. What you should notice here that when M is large, this goes to 0. So the first thing I want to do is prove this concentration inequality for Gaussian random matrices. All right, and that will be on the board. There will be a fair amount of things on the board today. So first of all, concentration inequality. So, okay. Let's see. Yeah. So again, the entries Aij of the matrix are some Jij of the square root of m, where each of the Gij are normally distributed, mean zero variance 1. So I always use the letter G to denote a normally distributed random variable. Standard 1, and so they are independent as well. So I fix a vector x in Rn, and so I want to look at, first of all, at the probability that A of x in L2 norm squared is larger than, say, 1 plus t times the L2 norm of x squared. I've got t in 0, 1. Okay, so I'm going to work with that. I'm going to show that this probability is small. So it is a probability. So let's just recall what we wrote. Maybe I guess I should write it once more. A of xi, that was the sum of the aij xj, j from 1 to capital N. And we did say that this is Gaussian, right? So I'm going to call that, well, a multiple of so it's mean 0, it's Gaussian. We have to just find the standard deviation of this, and we said that we have the norm x that comes into play, and then the normalization square root of m, right? Ji are independent, again, standard normal random variable. Okay, so that was somehow on the slide before. Okay, so now here, when we look at that, this is the sum of the square of that, so it's x squared ji squared over m. So that's exactly this. Well, what is the probability? Doesn't matter if I put a strict inequality or not here. 1 plus t x squared. Okay, again, this event is, there's a sum that should appear right, from 1 to m. It is also this event under the probability is equivalent to saying that, so simplified by the norm of x squared, get this m on the other side, so the sum from I from 1 to m of ji squared is larger than m times 1 plus t. And I hope I'm not forgetting anything. This is what it should be. Okay, so we want to bound this probability that the sum of square of Gaussian is larger than this here. So one way to do that is to say this inequality is the same as the inequality if you apply to both sides an increasing function. In particular, we're going to take exponential of u times that for some u positive to be chosen later. Right? So I'm going to take here u positive to be chosen later. And so rewrite again this event here as exponential of u times the sum of the random variables larger than exponential of m times 1 plus t. And there is a u that's missing here, u m 1 plus t. The advantage of the exponential is that the sum will transform into a product. Now, we use here, this is where we bound something, we use Markov's inequality, which says that the probability that a random variable is larger than some threshold is smaller than the expectation of the random variable over that threshold. So I'll take that for granted. It's not too difficult to obtain. If you have not seen it before, you can find it in many books. And you see it's quite easy to get. So less than the expectation of this over the threshold here, u 1 plus t. Now, we've got, as I said, the exponential transform this sum into a product. And I can write the denominator as well as a product of m terms, which are the same. Okay, now those random variables that appear here are independent. So the expectation of a product of independent variable is the product of the expectation. So here, using the independence, I obtain that this will be equal to the product of the expectation of u j squared over the product plus t. Now, I will have the product from 1 to m. So exponential of u 1 plus t. So the you need to take for granted the Markov's inequality. Also, what I'm going to take for granted is the expression of the moment generating function of the square of a Gaussian. So does anybody happen to know that? It's not a too difficult calculation, but it's 1 over square root of 1 minus 2u. You would simply calculate it as an integral of exponential of ut times the probability density function of the Gaussian, which has exponential in it, combine the exponential, make some change of variable, it comes out. Okay, so now I'm here. So, in fact, this term does not depend on m, so it will be raised to the power m. Okay. Now I want to bound this. Remember that I want to, at the end, obtain exponential of something negative times m. The times m will come from the product of m terms. So I want to say that this is less than exponential of something negative. So basically a number less than 1. All right, so, but I want to work a little bit on that. And we can do it in the following way. So that's a power 1/2 of let's write so 1 over 1 minus 2u. We're going to write 1 as 1 minus 2u plus 2u. So we're going to get this. Okay, and 1 over 1 minus 2u is 1 plus 2u plus something else when you expand it in as a series. But you can, in fact, when u is small, find a bound, a correct bound, so that will be less than 1 plus 2u times, so probably 1 plus 4u if u is small enough. Small enough means what in that case? So if I want that 1 is smaller than 1 minus 2u times 1 plus 4u, which is 1 plus 2u minus 8u squared, so I need 1 minus 4u to be positive, so I need u to be less than 1/4. So this is valid for u less than 1/4. So now I'm going to use here that 1 plus something is less than the exponential of that thing. So less than the exponential of 2u times 1 plus 4u to the 1/2. Exponential to the power 1/2, so the power will come inside, we'll simplify with the 2. And if I expand the inside, so u times 1 plus 4u, so it will be u plus 4u squared. So this 1 over square root divided by exponential of u1 plus t is smaller than exponential of u plus 4u squared, and then minus what I have inside this exponential, so minus u minus ut, and so we've got this cancellation plus u negative u. And this is now that I'm going to optimize over u. Right? Remember, u was something that I need to choose later on. Still, it is fixed. I want to optimize u in a way that this quantity here becomes negative inside the exponential. Now, what is the optimal choice of u? Right, if you look at that, this is a parabola, turn upwards. So the minimum will occur when the derivative is 0. So when hu equal t, so when u equal t over 8. So that's the optimal choice. And so in that case, what do I get? Exponential of, so 4, so I've got t squared, I've got 4 over 8 over 8, so 1 over 8 times 2, 16. Minus u squared over 8, so u minus t squared over 8, sorry, and t squared over 16 minus t squared over 8 is minus t squared over 16. Okay. So overall, what I obtain is that if I look back at the very beginning, this tail, well, this probability that a of x squared is larger than 1 plus t times x squared is less than, so we first arrive at this product here. Each element in the product, they were all the same, are bounded in this way. So when I take that m times in the product, I've got minus t squared m over 16. All right, also, it's exactly the same calculation, but the probability that ax squared now, in fact, is smaller than 1 minus t times x squared will be smaller than exponential of minus t squared m over 16. Just the same calculation. And so when you put those two together, you obtain the probability that a of x squared deviates from x squared by an amount t times x squared that will be less than 2 times exponential of minus t squared m over 16. Oh, by the way, to be perfectly correct, I should have checked here that this is indeed smaller than 1/4, but it is. T is less than 1. Any questions on this proof? Okay, and can I drop the board down? Has everybody written what they wanted to write? Okay. So we arrive at the concentration inequality for Gaussian. By the way, for other types of random variables, that will still be true, and the argument is somehow the same, except that you lose some of the nice closed form expression that we have for Gaussians. But it's the same idea. All right, so where do we go from there? We use then covering arguments to prove the following. So you take again a random matrix that satisfies the concentration inequality. So, for example, a Gaussian random matrix, and fix a support set S for now. So we fix a support set of cardinality S. We're going to prove that the probability that AS transpose times AS minus the identity, the operator norm from L2 to L2 of that, the probability that this is larger than some delta is smaller than, so 2 exponential of a constant times delta squared times m. So with a provision is that m should be in that case larger than s times a constant and then a scaling in 1 over delta squared. Right, so the argument will use the following fact. So if you take a subset of the unit ball in Rk, K will be chosen to be S for us, or we can simply just take the unit sphere, think of that as the unit sphere, and then some norm, which will be the L2 norm, but doesn't have to be the L2 norm, as a covering number. So the covering number of the set U for that norm, and then with a parameter rho, is the minimal number of points that you need so that every element in U is closed within rho to an element in this set, in this net, right? So the minimum number of points so that every other point in U is close to that set within epsilon or within rho. All right. And so this covering number can be bounded by 1 plus 2 over rho to the power k. And I guess maybe I will explain that later if I do have time at the very end. But I'm going to take that for granted and use the other board to prove this assumption here. So we take A, this random matrix, to satisfy the concentration inequality, and let S a subset of 1n with of size S, little s be fixed. So I'm going to take rho, this parameter that will define the covering number. We will see in the proof what it should be. So and let, say, U1 up to UN be a rho net for the sphere of the set of the space of vector in Rn, but which are supported on S. Okay, so we've got a linear space of, in fact, dimension S. There's only S, 3 parameters there. And so we consider the sphere. We take a rho net for the sphere, so we can take the cardinality of this rho net by what I said before to be smaller than 1 plus 2 over rho to the power S. Okay. So what we want to establish that the norm of AS star AS minus the identity from L2 to L2 is less than delta, so with high probability. So for ease of notations, I'm going to call that B, this matrix AS star AS minus the identity. Okay, so we know that what we know is that we can apply, the concentration inequality to any fixed vectors. So we're going to apply to any vectors in this epsilon net. So with high probability, so with fail. Okay, let me write it in this way: the probability that B of UI, and did I say I work on the sphere? Yeah, so I'm going to take T here. T is probably going to be delta over 2 in the end. So why can I write something like that? Let's first look at if I is fixed. Right? If I is fixed, when I write B of UI, where B is this, this in fact is AS UI, or in fact I can remove the subset S because UI is supported on S. So this here is exactly the same as that. And T is the same as T times the norm of UI because UI is on the sphere. So in fact, for a given I, the probability here is smaller than 2 times the exponential of minus C T squared M for a given I. Okay, this is the concentration inequality. Now, by the union bound, this happens for some I with probability at most n times that. Okay, I hope everybody is with me here. So it's less than 2 times n was smaller than 1 plus 2 over rho to the power s times exponential of minus c t squared n. Okay, so we're going to place ourselves in the very likely event that b of ui in a product ui is smaller than t for all for all I. That happens with probability 1 minus that. Okay, so let's place ourselves in the likely event that b of ui is less than t for all I from 1 to n. Okay, the probability that this event fails is bounded by that. Okay, so now we're going to fix or take x in the unit sphere of that set here. So what I want to prove is, in fact, that b of x in a product x is smaller than maybe t or 2t, probably. So we're going to take x in the unit sphere of x. And so because u1 up to un is a row net for the sphere, we can choose some I such that x minus ui in norm is less than rho. Okay, so then I'm going to look at b of x in a product x. And so x is close to ui, so b of x in a product x should be close to b of ui in a product ui. All right, so what's left in this term here, I can write that as b of x plus ui, x minus ui. Is that true? Well, when I expand this inner product, I've got bx inner product x, which is here. I would have, so bx with negative ui and b of ui with x positively. And because b is self-adjoint, those two are the same. So they cancel each other. And then I've got minus b of ui with ui, which cancels with this one. So this is indeed correct. Right, so I want to look at the absolute value here. So that will be less than. Okay, I shouldn't do that, but I will do that on the board. Do it right now. Okay, and b of ui in a product ui is less than t. The second inner product will be less than the norm here times the norm there. So the norm of that will be bounded by the operator norm of b times x plus ui times x minus ui. Okay, so bounded by t plus this norm, so that is at most 2. Each element has norm 1. So here, the 2, I put it in front. And x minus ui is less than rho. All right? So that is true for any x in the unit sphere of S. So if I take the maximum of the x, over x, what is the maximum of the quantity here? is actually the operator norm of B, because again B is self-adjoint. And that was always smaller than T plus 2 operator norm of B times rho. So I can get a bound for the operator norm of B from there if I make rho small enough at the beginning. So then I can put that on the other side and bound it by 2. So in fact, that gives you that the operator norm is smaller than, so it will be T over 1 minus 2 rho. Right? I want to make sense of that. So at the beginning, I will choose rho less than 1/2. So maybe I choose rho equal 1/4. And then that becomes T over 1 minus 1/2. So T over 1/2, so it's 2T. Okay, and I want maybe 2T in the end to be delta, meaning that I choose T equal delta over 2 in here. Right. So what I did obtain here eventually is that the operator norm of B, which was my objective, the operator norm of B is less than some prescribed delta at the beginning with high probability. So what is the probability? If we look back at what we've done, the failure probability of this event is so smaller than that with the proper values of rho and T. And so it's 2. So if I plug in rho equal 1/4, I've got 9 to the power s. And then here I've got exponential of minus a constant times T squared times M. Well, T is delta over 2, so I will have delta squared over 4. Let me call that another constant. It doesn't matter really which constant it was. But overall, I get 2 times exponential of log of 9 minus this constant times m. So now what I want is that this exponential is in fact of the form exponential of minus something times m. So what I just need to do is make sure that this term here that I subtract is more important than that one. Right? So I will make sure that so maybe that this term is smaller than half of that. So ln of 9 smaller than 1/2 of C prime delta squared over m. And yeah, there is an S missing. It's from here. Yeah. So S is here. So it will be less than 2 times. So that's less than 1/2 of it, exponential of minus C prime over 2 delta squared m. So high failure probability or small failure probability, provided that m is larger than some constant times S over delta squared. All right, so the idea of the covering argument, maybe to sum up, is to apply the concentration inequality to a net on the sphere and approximate each element with the closest one on the sphere and just work with some triangle inequality to at the end, obtain it not only for the net on the sphere, but for the whole sphere, where you change a delta over 2 to a delta in the end. The fact that we're working with the L2 norm and self-adjoint operator here gain us something a little bit, because we can do this little use this little identity. Otherwise, you can do that for any kind of norms, but you would get, instead of a delta squared, you probably get delta times log of 1 over delta on top of that. So that still allows us to get the optimal scaling in 1 over delta squared. Okay, so concentration inequality, covering argument. The last step is a union bound, but the last step is really, really short. I'll do the break right after this. All right, so now A random matrices satisfying the concentration inequality. The probability that delta S is larger than delta will be smaller than something, decaying exponentially in M, provided that M is larger than not only S, but there will be the extra log factor, log of En over S, coming into play. Let's see if I wrote the argument down. No. But so the argument is, okay, so what we've obtained is given a fixed S, right? Okay. Recall that this is saying delta S was the maximum of the whole subset S of the operator norm for which I just derive a probability bound. Right? So this is saying that this previous operator norm is larger than delta for some index set S. So now you use a union bound, and what comes in front of the exponential of minus delta M for delta squared M that I've just obtained is the number of subset of size S in 1 up to N. So N choose S. And so I want to work with that. What I'm going to use is that N choose S is smaller than En divided by S to the power S. It's also larger than N over S to the power S. So we use this little inequality to have basically to arrive at something of the type. So this binomial coefficient is less than En over S to the power S, and then we will have an exponential of minus C delta squared M coming into play. So under just one exponential, you've got, so that will be S log En over S minus C delta squared M. And just as I said, you want in the exponential these negative terms to win. So you make sure that this is smaller than half of that, and this is exactly saying that M is larger than some constant times S times log En over S. So the last step, the union bound, is usually not the problem. Just have to remember this little inequality that I will use later on as well. All right. So as I said, the arguments will be valid for other types of random matrices so long as it satisfies the concentration inequality. For Gaussian matrices, there are more powerful techniques that allows you to prove the restricted isometry property, where you can, in fact, estimate a bit more precisely the value of this constant. And so here's the summary, that the restricted isometry condition for sparse recovery are all of this type, but they guarantee stability and robustness of reconstruction in the following form. And they happen with high probability for random matrices in this regime of parameters. So as soon as m is of the order of s times log, you can put the en over s if you want here or not. Doesn't matter. So tomorrow, I will do something else after the break, but tomorrow I'm going to show that we cannot do better than this number of measurements if we are after reconstruction bounds of these types for any A for any delta. In other words, the compressive sensing results are optimal. So that's tomorrow. And in fact, I will not say anything about that tomorrow. But then after the break, I want to say a few words about other types of random matrices. So short break? Yeah. Unless you don't want to, I can go on. So I want to say a few words about other random matrices, but before that, maybe I'll take a computational interlude to show you, yeah, well, that in fact it does work, or all what I'm saying, and in particular L1 minimization. So if I take the size of the problem to be n to be 1,000, m will be 300. So let me first here define the sparse vector that I want to recover of sparsity 50. So here's the support, and I define it random on its support. I will take a measurement matrix, which is Gaussian. So round n in MATLAB produce the entries to be standard normally distributed, and m and n are the size of the matrix that is produced. The normalization I have to put divided by square root of m, as we've explained. Y is the observation on x. This is only what we will see. Y is a times x. And then there's a noisy version of it to see as well that I showed you the first day, an algorithm that seemed to do the work, but that wasn't stable or robust. But I've claimed here that L1 minimization, for example, is stable and robust, so we'll just make sure of that. So there are many algorithms for L1 minimization. It's a complicated field to know which algorithm is better than the other one. So I'm making no claim here. I'm just taking some algorithm that I have on my computer and looking at how they perform. So the first one is L1 magic. So the first one that was really devised for the purpose of L1 minimization, which is not something standard optimization package. So on the exact vector first, and here I'm looking at the norm of x minus the output of the algorithm. Should be 0 or fairly close to 0, and it is, well, we don't see it here. Let's see. Okay, so it'll work. All right, so of the order of 10 to the negative 6, it took, I was also looking at the time it takes, and the time is about 1/10 of a second. Okay, if we, with the noise that we've added, we can do the noisy version. So it's not as good, of course. We cannot get an exact reconstruction, but still it's not too bad. So with L1 magic. Now this is another algorithm, adaptive inverse scale space, that I happen to have, which should give the same result. It still does L1 minimization, and I'm using the same x, the same y, I don't know x, same a, so should give something fairly similar, but a little faster. The fact that it's much smaller, the error simply depends on what threshold you put for the algorithm to stop. So exact recovery again on the noisy vector. What was the noisy error before? 0.16. So it takes a little longer, but still gives you same results. Here is some sort of ersatz with, I think it's a little remark that I've done at some point, but really with, if you remove that 5 life of MATLAB codes and using some non-negative least square version of, it's implemented in MATLAB, you can do L1 minimization as well. Let's see. And fairly fast too. And with so the noisy version will give us, so it's a little slower in that case, but still same kind of results. So that's L1 minimization. Hard thresholding pursuit is an algorithm that I've mentioned as well. If we do the same thing, you will see it's again rather fast, even faster in that case. Still almost exact, exact by all, for all practical purposes. Reconstruction in the exact, when we have measurements with no errors, with some error, it is still quite good as well. I'm giving a warning that it converges to an incorrect solution in the sense that I can look at the norm of y minus a times the output. If it's non-zero, I say incorrect solution, but of course we cannot get a correct solution in the noisy case. Okay, so that was just a little, I guess, interlude to break away from the theory, and let's come back to the theory. So I'm taking. All right. So what am I saying here is that an important class of random matrices that also satisfies the restricted isometry property are partial Fourier matrices. It means that you take first a big n times n discrete Fourier matrix, and then you select rows at random. Right, so there's still randomness here in the way you select rows, and that will satisfy the restricted isometry property, provided that m is larger than, so you see s, you see the scaling in del k squared. The log factor is a little different. First of all, it's not log of n over s, it has to be log of n. And the power is not 1. People believe it is 1. I think the power 3 is the best that's out there at the moment. But you get the same time of those matrices also satisfy their IP, and they're more important in practice because they have fast matrix vector multiplication. So in the algorithm, it's actually important. They also appear in MRI, those kind of measurements. So it's an important class of matrices. So I deviate for the classical notion of restricted isometry property, but if we were to look at Gaussian matrices satisfy the restricted isometry property, Bernoulli matrices as well. At the other end of the spectrum, there are matrices with Laplace random entries. In other words, the property density function, instead of being like exponential of minus t squared, is exponential of minus t. Well, they don't satisfy the IP in the optimal regime of m, like s of times log to the power 1. They do with a log to the power 2, I believe. However, they still do satisfy the null space property. And in fact, the way you can see that is that they do satisfy some sort of restricted isometry property, with the difference is that the inner norm, you don't take it to be an L2 norm, you take it to be an L1 norm, for example. And the outer norm, in the most general case, will depend on the property distribution you've considered. It's not necessarily the L2 norm. It is exactly the L2 norm in the case of Gaussian matrices. But in general, it is just comparable to the L2 norm, meaning the ratio is bounded by two constants, from above and from below. the thing that I want to possibly look at for the rest of this lecture are something completely different, are the adjacency matrices of lossless expanders. And I'm going to explain what that means. But basically, they do satisfy restricted isometry property in L1 for the inner norm and from the outer norm. So for every sparse vector, you get that kind of inequality where you can make delta theta as small as you want. Okay, so I want to finish with explaining this a little bit. So a lossless expander is a bipartite graph. So it will go. We will have capital N nodes on the left and little m nodes on the right. Every node on the left will be connected to D nodes on the right. In fact, it's left regular, D regular. D regular, left D regular simply means that every node on the left is connected to D nodes on the right. Okay, so that's a left irregular bipartite graph that I've shown. It's not a lossless expander so far. So the lossless expander will come from the property that I'm going to write here, is that for all J is some more, let's say, S, why not S, an index set from 1 to n, so a subset of 1, 2 up to n with a relatively small size. We want that the so I'm not going to write explicitly what this is, but this here, those are the right vertices connected to the set S. So take a set S and connect each element to its right vertices and take the union of all of those. So you've got a set of right vertices connected to S. So what is the size of that? Well, since each element in S is connected to a D element to the right, the size can at most be D times the size of S. Okay, and we want to be close to that. Close in the sense that we want these to be larger than 1 minus theta times D times S. Cardinality like that. So that will be called, let's say, give the parameter. The parameter here are D, S, and theta, lossless expander. It's a left D regular bipartite graph satisfying this property. Now, whenever that happens, this L1 restricted isometry property that I mentioned is satisfied. Well, can it happen? It's a big question. Here is the so most left D regular graphs are the S theta lossless expander provided So that m is again of the order of s times log En over s. So there is a constant that will depend on theta here, the same way as the constant depending on delta for the classical restricted isometry property. And also we have to choose d carefully, but then I don't remember exactly what it is. Olga, do I have time to go into that? Do I have like 10 minutes or not?
Well, 5 minutes, enough.
All right, we'll see how it goes. All right. So what is the number of left d-regular graphs? Well, for each element on the left, you have a choice of m choose d element on the right. And then you have n element on the left. Okay, so a left d-regular graph fails to be an expander if and only if. So what does that mean? It means that there will exist, J, so J is stands for S here, included in 1 up to n. So let's call little j its cardinality. And of course, we're not going to take it doesn't fail for things of cardinality 1, so j is in 2 up to s, such that r of j is smaller than 1 minus theta times d times j. And that I can also write as the fact that there exists an I in the set of right vertices in 1M with the size of I is 1 minus theta dj. Let me call that rj and pretend that it is an integer. Otherwise, I have to put I have to think if I have to put ceiling or floor or things like that, but it says the same idea, so such that r of j is included in I. Okay, so number of left d-regular graphs failing to be an expander. So basically, if you look at this property, so it will be smaller than, and then if you look at this property here altogether, if you have a fixed j and a fixed I, how many graphs will satisfy this condition here? Well, what we're saying is that on j, we are not taking the right neighbors from 1 to m, but only from I. So it means that we need from I as size rj. So we need to take d elements in there for all the elements that are in j, and j as size, what was the size of j? Well, j. And then outside of j, I have total freedom, so m over d to the power n minus j. So that was if I and j are fixed. Now I need to vary I and j as well. So how many subset I can I have of this size? So it's subset of 1 to m of size rj. How many subset j of this type do I have? So subset of 1 up to n of size j. And then also j is free to vary between 2 and s. Right. Trust me on this, and check it later. So the proportion of failing of graph failings to the expanders so this proportion will be this of the total number of graphs. So it will be the sum from j from 2 to s of some pj, where pj the explicit value is. So when I'm going to divide by n choose d to the power n, that power n will disappear. So we'll have nj, mrj. Then I will have something to the power j, which will be rj over d. And I will also have m over d at the denominator, all of that to the power j. Okay? So I want to show that this is smaller than something. That is smaller than 1. I mean, in fact, I'm going to use that with probability epsilon, given epsilon, if I choose m correctly, that will happen. So it's, well, you have to know where you're going with that, but as the ingredients at this point are only the bounds for the binomial coefficients that I've shown you before. So that will be less than en over j to the power j, m over rj again, which I pretend is an integer. There's an e here. So in this ratio, the numerator is less than erj over d, so to the power d. The numerator is larger than m over d, so e does not appear to the power d, and then that's taken to the power j. Okay, so I think I can finish in a few minutes now. Maybe I've already taken more than 5 minutes. Do you want me to finish or not? I'm waiting for just one yes. Okay, well, open probe, yeah? Exercise. Okay, quickly, very quickly then. Pj less than. So what will we get? So I think this does not change. So if you look at the power, so we have e to some given power here. E, what is the power of e that we get is rj plus d times j. And then we have the quotient m over rj. And that comes to the power rj first. And in fact, I'm going to write it rj over m, because that will come with a positive power. So we've got the rj first, so that will have to come with a negative sign. And then over there, it's dj minus rj, right, if you make the simplification, because d to the power d, that goes away. So rj plus dj, I think it's 2 minus theta times dj. Rj, or dj minus rj is theta dj. And I'm going to take now, I want to make this exponential of 2 theta dj disappear. So in here, I'm going to choose m carefully. Carefully, I think, means m is 2 to the e to the power 2 over theta times d times s. Let's see. So here I would get rj is smaller than Rj is 1 minus theta times dj, so smaller than dj. M larger than e to the 2 theta times ds. So to the power theta dj. I remove the d. I will have e to the power 2t over theta divided by theta. So it's in fact be e squared times theta dj. That will in fact, yes, disappear with that. And I get exponential of, so e and g to the power g. So there's something disappearing here. And then I've got j over s to the theta dj. Okay, maybe I'm not finishing at this point. This was the important thing to do. The choice of m. Again, pretend it's an integer. Then here, the next step is the choice of d. And the choice of d, you want to make that. So already you're going to remove. Now you've got j everywhere. You can put the power j outside. And then you will have theta d. So you want exponential of theta d in the end to basically cancel that. So you want it to be like En over, I think, epsilon s, where epsilon is a targeted probability. So if you do that, basically d is the 1 over theta times the log of n over s. Right? So d will have log n over s. So m will have s times log n over s. I'm not finishing, so home exercise, basically. Right? But that's one way to there are other ways to show that most left regular graphs are lossless expanders. That is the most natural if you think that the random model is to take each set of right neighbors uniformly at random. But unfortunately, what you get is a constant that depends exponentially in 1 over theta, and that's not so good. So if you change the model for choosing the random graphs a little bit, you do obtain better results. And I'm going to finish on that. Once again, tomorrow I'm going to prove optimality of all those m of the order s times log n over s. Thank you. And sorry for